Hey guys, Rudy, welcome back.
Yeah.
Hey Henrik.
Hey,
How are we all doing? Good week so far? Almost Friday. Oh, only like that. Not enough walks? Haven't been getting fresh air or what?
Too much sitting in front of the computer. But well, that's the price for studying IT and physics.
Yep, got to do it. I think we all probably suffer from that a little bit. I do really miss my my old standing desk. I used to have one that would move up and down.
yeah, it's very
And
handy.
are you at one?
Yeah,
Okay.
I got the button and boop, boop. Yeah.
Nice. Okay. Yeah, I can actually kind of tell your posture is much less like this than everyone else.
Yeah, no, that's why I took the facing camera as well. You're right. Yeah, but I find it really useful every 45 minutes or an hour or so to kind of move. I don't usually during the lectures, but yeah, otherwise definitely.
All right, we're flowing in. Hey Rati, hey Kirti.
Hi everyone.
Hi.
And we have a new participant, Aloysius. I remember you from the intro to token engineering session. Is that right?
Yeah, correct.
Yeah, awesome. You found your way into a research group in 2 days. That's impressive.
Sweet.
Yeah, welcome.
There's
Yeah.
so many things that happen in the comments. It's kind of
Yeah.
hard to see it all. There's lots of calendars.
Yeah. Oh man, could say that again. Okay. Well, I don't want to delay for too long because I think we do have a lot to cover today. So it might be good to get started, and in the next few minutes I'll obviously still be letting people in. So yeah, then I guess today we have the lecture on parameter selection under uncertainty. Exciting topic. And Jumpsheet and Chris, I think, are going to be trading off. So we'll have a lot of action to follow along. And yeah, Jumpsheet, I'll hand it over.
Okay, thanks. I'll go ahead and share up. Hopefully you see my screen. Slides are coming through.
Yep.
Excellent. All right, well, welcome to the final of the formalized lectures, let's say, for this first part of the course, where we've been tracking this engineering design process workflow, all the way from inception and ideation into designing what a system is, looking at what a system is, then describing its formal properties in such a way that it can be then placed into a context that is computable and as an implementation, as we saw last week in cadCAD. And what we're going to do now today is to wrap up the usefulness or the utility of that progression up to the point of understanding how to match the system goals that were originally part of the ideation process for the system, and how its outcomes are determined by what you select or actually choose to design. And the way in which this part of the workflow operates is to take seriously the computer implementation as a way of parameterizing mechanisms that are supporting system goals in a well-defined way I'll mention, and then performing some kind of an optimization or selection of the resulting parameters that then in some sense, trade off one system goal for another or one metric or KPI for another, such that the system itself is behaving as intended or as desired. So I'd like to start this with, from today's agenda, starting with an idea that's sort of that arc that we've been doing, kind of tying together everything we've done from from the ideation into especially the math spec and how we got to the implementation, and then describe how we would start doing computational science on the basis of that. Then move into the formal workflow parameter selection under uncertainty. Then Chris will take over and show you how to apply that methodology to the Hydra AMM's cadCAD implementation with a few examples. Then he'll kick it back to me and I'll describe one of the ways in which we can identify how to design mechanisms. It's one of the things we kind of left unsaid. And there's been some discussion in the Discord and I think in the Tuesday sessions over things like invariance. And so I'll introduce just the merest bit of the tip of the iceberg of that, but within the context of one of the mechanisms that's very interesting for this AMM to be studied, which is the fee mechanism. And then we'll finish up with a small bit on my part, and a small bit from Peter on where we go from here. How we're going to progress into the following sessions, 7 through 12. Okay, so moving from the system narrative to the math spec has imbued us with all of this structure. What we've done is we've been creating this entire formalization of what people said they wanted a system to do, what the stakeholders have said they would like to have, into a kind of a blueprint of what it is we can put into a computer. And that blueprint, don't forget, was called the mathematical specification or the math spec. And the implementation that we have shown throughout is via the open source tool cadCAD. And the outcome is this ability to have an implementation that is amenable to answering questions about the system without necessarily going to the real world and grabbing things and saying, but what about this or what about this? So we're looking at things in which we can isolate it in terms of how the model has been created and reflective of the system goals. How can we answer questions that we find interesting that these system goals themselves have both elucidated and are also based upon? So the math spec itself sets out the formal structure that you need in the blueprint. And while doing this, it actually lays bare any kind of gaps in our understanding about the complexity of the system itself that has a feedback to the system goals that we care about. So I'll give a couple of examples within the AMM style, AMM context, just to kind of give a connection between what it means to have a mathematical specification that informs us about questions. Why would a formalization source questions for us? Well, one of the things that happens when you write the whole math spec down is you have a whole bunch of transition equations. Remember how the state is changing over time. And so what you might start to immediately see is, well, I see these as state transitions from one point to the next, but what does this tell me about how the system is stable or unstable overall? So for example, you might think of yourself, well, when does the system itself actually stop performing in some way? When do the state update equations lead to runoffs to minus infinity or infinity? When does the system crash? And what do we mean by a crash? How do we think about that question? How do we test a crash? If we were looking at it from an AMM math spec perspective, we would say, well, we've defined reserves and we've defined prices and we've defined mechanisms like the swap mechanism. But we haven't said anything in the math spec about the reserves remaining positive for any sequence of trades or swaps, or anything about whether or not the prices themselves remain reasonable as prices. In other words, perhaps remain finite or don't go to zero for any such sequence. And so more generally, what you're thinking about as you're writing down the formalisms is attempting to tease out under what conditions the system fails. And that will give you some indication as to how the system remains stable for those parts of the system under scrutiny or for those types of admissible actions that you are looking at or testing or questioning yourself about. Another example is system participation. Do users have an incentive to participate in the system? Is it if you build it, they will come kind of an argument, or is there something you want to tease out more formally about whether or not people will actually use the system as you expect? In other words, will they participate to reinforce the system's goals or properties, or will they participate to undermine those goals or even destroy the system? And again, looking at it from an AMM perspective, we've defined entities that interact in the system, like the liquidity provider and the trader, for example. And in particular, for the liquidity provider, we've defined the add and remove mechanisms But we haven't said anything about whether or not a rational liquidity provider would participate in order to provide liquidity. Is there an incentive mechanism that is present there? That isn't something that has been necessarily defined at this stage. Would a rational LP participate in order to exploit the network or attempt to recoup gains that in itself would actually shut the network down, destroying the gains to trade from traders, for example, who are using the liquidity facilitated or provided by LPs to conduct exchanges? So again, the abstract question would then be more generally, under what conditions then would the participants act to support the system goals? So we have global questions about system stability and its movements, and then we have more specific or refined questions about the participants themselves. And these are all questions that we would like to have a computer implementation help us to answer or to identify directions in which we can gain an answer to these questions. Now, it's important to remember that although we're teasing out these kinds of questions from the formalization itself has limits because it is, in essence, a scaffolding or a blueprint, and it doesn't do more than it's advertised to do. So it's not able to answer questions that it's not intended to answer. Instead, it creates a backdrop for the questions from business logic decisions, things like participation incentivization that can be formulated within that context. So this creates a dependence upon some of the parameters that the computer implementation has created in order to explore how to answer the questions that stakeholders and others have gained from looking at the formalism. A math spec doesn't provide a single analytical closed form parameter recommendation because the parameters themselves haven't been selected or assessed at the stage of the math spec. What it does instead is say, well, given the fact that we have these kinds of variables that are available in the computer implementation, we can move forward to create ways of assessing different constellations of these parameters as good or bad, or as supporting system goals, as not supporting system goals, as providing system stability or detracting from system stability, and so on. And that's the focus of today's session, is this notion of, okay, given the fact that we have this way in which we can parameterize the system, how do we go about actually selecting the parameters that fulfill some criteria? Now, that's not the only source of questions that are to be answered from the formalization of the math spec. That's a technical way of looking at the system as defined and saying, okay, what are the things we care about or are we interested in? Thought experiments, of course, at the very beginning of this whole process, even from the ideation phase, from the phase 0 or phase 1, are really useful because they define the informal system goals that then lead to questions. And those questions are often, although not exclusively, formulated as what-if thought experiments. And you say, well, look, we want to have these scenarios that we're trying to describe, things that can occur in the system. And we'd like to understand exactly the interplay between, for example, participants in the system or the environment in the system to be able to understand questions that are within these scenarios. So a couple of the AMM-centric examples again. If an AMM pool is operating on Ethereum, an informal thought experiment question would be like, well, what if gas costs increase dramatically? This is something which is relevant for any systems that are built on Ethereum. It's a what if question, and then you can build and tease out how you might test this in an environment that you have built, a cadCAD implementation, that is attempting to model this system that's on Ethereum. As another example, if an AMM pool operates within an ecosystem of other pools, so that other pools are actually performing or facilitating the same service that an AMM is facilitating, the question would be, well, these are my competitors. What is it that they're doing? What if they're actually offering a better deal, a greater return on yield, for example, to providing liquidity? What are my response dynamics? How should I be designing the system so that with a certain amount of confidence, most of the time I'm not being undercut by another system? So these are, again, thought experiments that come out of the delineation of or the hardening of the system goals that are being articulated when the system itself is being defined. Now, from each of these two types of locations of sources of questions and their associated scenarios, you can create what we call a testing grid to be able to take the actual computer implementation and in a systematic fashion formulate the way in which the questions that are raised can be answered. So you detail the questions, you detail, in fact, the simulation scenarios under which those questions are going to be encapsulated. You examine the parameters that you expect to be impacting upon that particular question in terms of its answer, and then the ranges of those parameters that you're selecting over. And this formalization becomes this parameter selection under uncertainty process, but it hinges upon being able to formulate the questions in such a way that a computer implementation can answer them. And just as an example of a testing grid, and I think that Chris will show you one specific to the Hydra AMM, this is a very general one that is kind of operating in the AMM framework. The questions are in the first column, things like, do we have efficient price changes? Does a trader get what they expect? Again, very loosely defined. Do LPs earn enough yield? And then within the scenarios, you start thinking about how to model answers or the framework in which answers can be found to questions like this. So for example, the sequences of trading frequencies and sizes would help you understand that is a trader getting what they expect. For the LP, that depends upon fee specifications in addition to how individuals are using the system. Once you've got the scenario runs figured out, it tells you kind of what are the things that you would like to change between different experiments. Then you're going to look at the different parameters that you can select or the degrees of freedom that your mechanism design affords you. So these are the parameters that are not calculated or fixed in stone from the math spec, but rather each parameter value represents a different mechanism that fulfills the requirements of the math spec. And so then the goal is, out of all of these different particular members of the class, you're trying to pick out that special parameter that perhaps fulfills the system goals and answers the question under scrutiny. And so here, for example, there's a list in the third column of different parameters that might be expected to be impinging upon the answer to this question. And these are parameters that can be both the mechanisms internally to the system, but also can be things that are coming from the outside. If we're modeling external processes as stochastic processes, for example, then we would want to be able to know how to do this. What would we be looking at as particular classes or ranges of these parameters? And that's the fourth column. So we drill down a little bit from identifying, for example, the arrival rate of trades, and then we specify the ranges that we want to sweep over. For example, if we're using a Poisson distribution or a normal distribution, we would be sweeping then over the parameters of these distributions. So this builds for us kind of a lookup table or a recipe book, in a sense, for experiments. And it allows us to complete this arc of going all the way from the narration about this system should be doing stuff, all the way over to, well, what is it exactly that we want the system to do? What is it that we really want to avoid the system doing? How do we want to ensure that individuals are using the system as intended? All of that then comes into the context of building this testing grid, and then being able to apply a workflow to select optimally the parameter values that will then answer these questions to some degree of satisfaction or to some level of assessment. Okay. Any questions before we move on?
Henrik just dropped one in the chat. Henrik, would you like to?
Yeah, it's more like, I mean, if you don't have data and you're testing here, how do you actually determine which distribution to apply to whatever parameter value you want to investigate further?
Yep, so it's a good question. For external processes, you typically will try your best to find data that will give you some indication as to a distribution that seems that it's being pulled out of the system as providing explanatory power. You can do so by fitting distributions that are parametric, or you can do non-parametric estimation of some sort and then kind of tease out the underlying parameters from the fit that happens. You can run a regression to try and find parameters values that you then tease and manipulate within the system. So for stochastic processes that come from the outside, you can look for analogs, or you can actually use some sort of, well, we don't really know, but we're going to try a distribution that gives us a fairly wide type of outcome. So maybe lots of different types of outcomes can be put into, for let's say, stock prices for a log normal distribution. We can't tell anything more than that, but we'll try to cast a fairly wide net over alternative parameter values that we'll be sweeping over, that we'll be searching over for the first 2 moments of that distribution, for example. Internally, The mechanisms that are derived for things, for example, like the swap mechanism or the add remove liquidity mechanisms, these are being designed to fulfill certain requirements. Remember the requirements that we used from the GDS that we built into the math spec. And then you have a parametric representation that usually comes out once you put this implementation into cadCAD. There, parameter values may have a sign restriction where you say, okay, I know this parameter has to be greater than or equal to 0, but I don't know anything further than that. So let me then select a grid up to a certain high value that maybe changes the dynamics so much that I know it can't be higher than this. And then within this, I just take a uniform distribution from there. So the different types of mechanisms give you different information. Whether it's external or internal also informs the distribution assumption.
And then you adjust if the results look weird or strange, and
right.
It eventually come up with something that you can trust. Or you
Well, what you look for yep, that's one way to do it. Another way to do it is to perform as wide a number of scenarios as possible, a lot of different repeated draws from different distributions, and then look and see whether or not the system has properties that are the ones that you want for a particular range of distributions. So you may have more than one distribution that comes up as a finalist, so to speak, but then you're looking then to see whether or not there's a parameter value that does equally well or good enough, quote unquote, for these different distributions, so that you're not locked into a single distribution.
But I mean, I was just thinking, because if you talk failure and stress testing as you were earlier, then I guess you're sort of way out in the tail. And it becomes very sort of crucial to pick the right distribution, I guess, or you will not optimize basically your business model if you either you're too risk averse or conservative, or you're too opportunistic and you stretch too much.
Well, there are two different distributions we're talking about here. So one of them is indeed the distribution of the run results themselves. And the more run results you do, the more draws from a given distribution you do, the greater confidence you have for things like risk trade-offs or risk management. In fact, one of the questions will come up in just a moment is what sorts of metrics or KPIs are adopted. And so something like a value at risk statistic can be derived in that fashion. The other type of distribution is the distribution that you are using from which to draw different types of exogenous processes that come in. And there, you're quite right. The argument has a bite to it, because if you have been assuming all along that the arrival process is a normal distribution where it turns out that it's bimodal, for example, and it really looks bimodal in the data, then that's something that you want to then, when you are taking your cadCAD model and assessing it for the parameter values that it has, take it to the data that is actually in existence and see whether or not it's backtesting well. And that's another section that we haven't, and we don't have time to go forward from this endpoint of parameter selection. There is another usage of cadCAD, of a cadCAD implementation or another computer implementation, which attempts to ensure that it is as closely fit to the live system as possible. And that's called a digital twin. And so a lot of the extant work that goes beyond what we're doing in this course involves actually tracking the live system and making sure that you can then go back and update those distributions in that fashion to ensure that you haven't mismatched. So it's a good point. Okay. So let me give you a, oh,
sorry, Kirti also had one quick one, I think.
Just one simple question: does the data have to be stable before we actually look at a good fit for some sort of a distribution?
It is one of those biases where you take data and you try to, when you look at data in a system and the system is working and has been working for some time, you try to find stationarity properties of it. One of the things that we will do to try to make that easier is to detrend data. Okay. But if it looks completely random or completely stochastic, with movements where there is potentially some argument to be made that there is in fact a changing underlying standard deviation, then you can build a hyperfamily on top of that and then sweep over the standard deviation over the variance to have some kind of movement of heteroscedasticity, basically just have time varying variance. So it's not something that you would necessarily lose fidelity over. You can do it. It's just that you would really need to ensure that the data is somehow telling you that it's necessary. Otherwise, you would try to detrend the data and keep it to a stationary series.
Okay.
Good question.
That's all.
Okay. So moving on to the actual process of this, the idea here is to figure out how to make cadCAD something more than just a curiosity that you've implemented and created, but that actually is an actionable machine that answers the questions we've been describing in the testing grid. And since uncertainty is inherently a feature of complex systems of this type, what we want to do is make a distinction, a hard distinction between things that we don't know, which is Knightian uncertainty from Frank Knight, into we know what it is that we don't know, which is something that was being described just a few questions earlier, which is the risk uncertainty, that we don't know the actual realizations, but we have an understanding of the system. We know what it is that we don't understand. And it's very important, again, and I've highlighted this before, and we've talked about it, Marlon and Chris, throughout the course, about assuring that we don't assume what we want to prove. And I include a pithy quote from Voltaire about doubt not being a pleasant condition, but certainty is an absurd one. So we want to make sure that we allow ourselves a degree of freedom to be in that risk uncertainty environment without either straitjacketing ourselves and saying we know everything that's going to happen, and without, on the other side, being so completely lost that we don't really know where to begin. That would be the Knightian uncertainty. So this workflow that I'm going to show you is a way of progressing from Knightian to risk uncertainty without stopping at risk uncertainty, without stopping at full certainty in the middle. Okay, and I'll go through each of these steps very briefly. And what follows, it follows a standardized engineering template that we apply to cadCAD. The first, which we've already discussed throughout, but we're now making more quantitative, is identifying the system goals that we want to articulate. We then look at the control parameters that are identifiable. Those are the things that are in the design process that are able to be set by the designer. Environmental parameters are then identified, which have to be assumed. This is the idea of the distribution that needs to be assumed, things that we know impact the system but cannot be controlled. Being able then to match the system goals as they're articulated to actual metrics that are derivable from the computer simulations or the computer experiments becomes important. These are the key performance indicators or metrics that need to be identified. When these four have all been set, simulations themselves can be conducted according to that testing grid, and then optimal parameters are selected. And optimality here has a particular interpretation, which I'll articulate, I'll define actually when we look at the system goals and the control parameters, because it's important at this stage to not expect that every single system goal is magically satisfied for a single parameter value. That almost, well, basically never happens for complex systems beyond some degree of complexity, even a low degree of complexity. So just starting with the system goals, this is just to ensure that the simulation parameters and the metrics are aligned with the overall objectives. So we go back and forth on the identification of the questions, of the scenarios, to make sure that what it is that we would like the system to do is indeed reflecting what the system goals are. From an AMM context, I'm just giving three examples. One might be price stability and reliability. You'd like the system to have prices that are relatively stable and are reliable in the sense that you believe that they are reflective of the value in the pools. You'd like a positive trader user experience. The traders actually use the system and enjoy the fact that they are getting something that they expect to get on the one hand, and also that they don't feel that they're somehow being blocked. And a positive liquidity provider user experience. And again, this may be articulated in the terms of their yield or their performance and the return on their investment. And each of these system goals is associated with one or more key performance indicators or metrics that come out of the system. So you're matching then, and it can be a many-to-one matching of these KPIs to system goals so that you have, in a sense, a quantifiable representation of what it is that the system is designed to achieve. Now, once you've got the system goals, you've been working throughout the math spec, the GDS and the math spec and the computer implementation to actually design the mechanisms that fulfill the requirements associated with those goals and the properties of the system. And that's led to control parameters. These are specifying those critical features that are selectable by you as the system designer in order to achieve those system goals. So they're the things the designer can directly implement. So again, looking at the context of AMMs, a swap or a trade fee is one such parameter. It affects the trader's user experience because it influences their cost of exchange, and it affects the LP's user experience because it affects the yield on their investment. There's also, for example, the initial liquidity, the reserve provision. How do you bootstrap the pool? That affects the price stability and its reliability, in particular short run versus long run volatility of the system. It affects the trader's user experience because it impacts initially how much of what they think they're going to get in an exchange is what they actually get, the slippage. And it affects the LP's user experience because there then becomes a very discrete difference between a short run yield and a long run yield, depending on how the system then progresses from that initialization. So these are just two examples of things that are able to be controlled and therefore have parameter values that can be adjusted to be able to fit different system goals via the KPIs and the metrics. Now, before moving on to the environmental parameters, it is important to underscore that control parameters generally don't support every system goal equally well. In fact, changing control parameters in one direction may have countervailing effects on system goal achievements in another direction. And so on the right-hand side, there's just a flow diagram showing that for different types of control parameters, they may influence different system goals positively, which are the green arrows, or negatively, which are the red dashed lines. And so if you move in one direction, if you're exploring this parameter surface by sweeping over different values, you may find constellations of parameters that seem to give you some balancing between the goals, but you're not going to find generally a single parameter constellation, a vector, let's say, that achieves all of the system goals to their satisfaction. And just as an example of when this might occur in the AMM context, if you were thinking, for example, of taking a trade or a swap fee and increasing it, well, the benefit, the increase, the system goal, which is being reinforced then is the user experience of the LP. Everything else equal, they get a higher yield because the fees are going into the pool and they have a share of that pool, therefore they get the higher return. But as you already know, the exchange cost of the trader then also rises, and that's a countervailing experience because then their user experience goes down. So you have this trade-off from a single control parameter in the direction of these two system goals. And then it's up to how those goals have been interpreted as metrics, as KPIs, to determine what one would consider to be an optimal control parameter for a given constellation. Now, environmental parameters we know are very important. They're the things that are coming from outside of the system, but they still affect the achievement of the system goals. So we can't control them, but we know that they're there, and we know we need to be able to provide modeling that is consistent. And as Henrik had mentioned before, we want to make sure we have consistency both overall in terms of the experimental setup, but also internally with respect to what it is that we think is the case for those exogenous systems that we cannot control. So again, in the AMM context, participant interaction, what type of transaction do they actually use in the system, or the intensity of the transaction through its volume is not something that is controlled by the system. It is something that can be modeled. And it can be, in essence, swept over. And Chris will show you a few examples of something like that. In addition, participant behavior is not something that we generally can fix and say, you will behave this way when you are using an AMM. You may have, for example, noise traders. These are traders who are making and performing transactions for reasons that we can't see. They're idiosyncratic. They're rebalancing a portfolio of their own. And we don't have any other information other than they make a transaction. As opposed to arbitrage trading, which is actually trading to an oracle price or an external price. And you can observe that when there is a mismatch between one AMM's price and this oracle price, that you see transactions flows from particular types of traders. So we typically try to model these using some sort of stochastic process for the external impacts, try to parameterize those stochastic processes, or try to build a black box which fits inputs to outputs, some kind of a system identification, where you're allowing the system some randomness to kick it, but you're trying to tease out some regularities from an existing parallel environment that may have similar properties. And so you may look for parallels that are out there already, AMMs that are acting in a similar fashion and attempting to tease out what kinds of modeling assumptions you need for those environmental parameters. Okay, and finally, you have the KPIs and the metrics. Given the environmental parameters, these control parameters are then selected according to how well these KPIs and metrics are reflecting the system goals. This is how we do this, the selection process itself. So how do we assess a good parameter constellation from a bad one? In an AMM context, once again, price error and volatility, so price stability and reliability system goal might be reflected in this particular type of metric that we can compute from the computer simulation. Slippage, the relative difference between the expected price and the actual exchange price, these support or influence both the price stability and reliability system goal and the trader's user experience. And finally, yield, the difference between the fee accrual and the impermanent loss that's experienced by an LP, well, that impacts both the LP's user experience and the trader's user experience. So these are all things that can be calculated and then linked to different system goals such that that balancing with the control parameters can be performed. And each of these KPIs can further be broken down into subcategories between time horizons, short run versus long run, looking at whether or not you're seeing just a particular kind or a height and absolute magnitude, or whether there's a variance associated with it. The way in which you are able to articulate these metrics in further and further detail provides a broader landscape for the system goals, which has complexity trade-offs. If you have too many metrics, then it's very difficult sometimes for parameter constellations to be found that support any of them. And so you end up with kind of a meh, we don't really know. But if you have too few, then you may find one dominates over another. For example, we find parameter constellations which dominate one particular KPI metric and the rest are left off to the side. So there is some art in terms of which of these KPI metrics are best reflective of the system goals that the system is designed to support. So the workflow, given these building blocks, is to specify the simulation scenarios in that testing grid to test against the system's goals. Once you've done that, you specify the generating processes for the environmental parameters, and you look for things like sweep ranges or distributional assumptions, historical fits, things like system identification, and so on. You then specify sweep ranges for the control parameters. What is the range of these values that you wish to actually investigate and look over? Perform simulations across all of these sweep ranges for the environmental parameters and the control parameters. And by doing so, repeatedly draw from the same distributions from those environmental parameters to create Monte Carlo runs. Once you've got that, for each of the results that you have for each of these experiments, you build a corpus of KPIs and metrics from these simulations. And this can be massive. I mean, we've had different projects. The Filecoin project, for example, had billions upon billions of these simulations that were being used, and billions of realizations that were then pared down and were then selected according to different types of criteria that were being used. That assessment process can be done in many different ways. Since you can't find a single parameter constellation that ranks all of the alternative system goals at the highest level, what you need to do is to perform some sort of internal or human-driven ranking, some machine learning between the parameters themselves and their importance, their relative importance in contributing to one or more system goals. We do some system goal landscape mapping to see whether there's a relative shift in the landscape of the system goals according to different parameter values. And then finally, qualitative analysis, just to see whether or not if we had different system goals, which are binary on-off switches, we would just test for different versions of this. And once that assessment is performed, then you would select optimal parameter values based upon this assessment process. Typically, we don't select single values. Usually what we would provide is a range and look for as small a range as possible. And so you see that this process itself could even feed back on itself. And after you found one range where you start to see some kind of support for system goals through their KPIs, you then narrow down the range, perform yet another sweep on that particular sub-range, and then do so again until you've got as narrow a range as you would feel is required for stakeholders or for your own confidence of understanding how well those system goals are being supported. But that process can become iterative, and as a result, you end up with that kind of ability to say, within this context, within this particular range, if you are then going to take the system and design it or push it live, there's a degree of confidence under which those system goals are being supported. Now, you may not be fully confident, and so what you would want to do is say, all right, given the fact that I have this range, what if I start swinging it around a little bit? How do I perform some sort of robustness assessment around this? And that allows for this fine tuning to be performed to see whether you've just found a parameter constellation which is on a knife edge. And that would be a bad thing. So you want to make sure you want to find that those parameter values that you found kind of has an open neighborhood where things themselves are fairly continuous from small deformations. That keeps the system from really relying upon that value too highly. And finally, once this robustness analysis and stability analysis has been performed, you then deliver the final optimal parameter recommendations along with these ranges, possible confidence intervals. If you've been looking at some sort of statistical distribution for the Monte Carlo runs, you could say with 95% confidence, we can say that these parameter values support these system goals via these KPIs. And that's the way that this workflow is designed to move from the whole question mark at the very beginning, what's the system for and why do we care, all the way down to this is how we have decided how to structure how this is something which is important and why we care. And here are the values of the mechanisms that we've created that support this system goal setup in a consistent fashion. Okay. Before I turn it over to Chris's part, I just want to take a breath here. I know it's a lot to process and digest because I've explained a process without actually going through it. But are there any questions kind of as either follow-ups from before or indicative of where we stand, at least in terms of how we've stopped at this point in the cadCAD usage process of identifying parameters?
Yeah, Henrik, feel free to jump in.
Yeah, one question. I guess if you're modeling from a sort of, say, your governance perspective, and we need to have the perfect OMNIPool Hydra set up, and it has to be stable, wouldn't you, whatever the output KPI is, wouldn't you also try to do some sort of expected shortfall analysis from the whole total of distributions, or is that included in what you're writing here?
It's included in what's being written here because it is indeed one of the KPIs that you can choose. Yeah. Okay. So we've got both value at risk, we've got expected shortfall as different types of statistics, both drilling down to within a system, within one particular distributional assumption, and then expanding all the way out to the entire scope. And certainly from the point of view of stakeholders, different stakeholders will have different familiarities, first of all, with risk management at that level, which sometimes we attempt to explain. We'll go through and say, okay, this is why you care about value at risk. This is why it should be one of your criteria. This is why expected shortfall should be one of your criteria. And then once having hopefully convinced the stakeholder that this is the way to look at the system, then derive the system such that they are comfortable with the confidence interval, the significance level that you've chosen. So if you're saying, look, we want this to be at a 5% or a 2.5% or a 1% or a 0.01% confidence significance level, then you make sure that you design the system so that you're actually getting as close to that fulfillment as possible.
Yeah. Thank you.
Yep.
And Paulina?
Hi, yes, this may be a little bit of a naive question because I haven't looked at the code properly yet. But so what information, coming back to what you said earlier about uncertainty versus risk, yeah, what piece of information are you feeding into these G functions, these decision functions for the agents in the system to make their decisions based upon? Or do you have a framework for that? Yeah.
You have two different ways you can do this. One of them is indeed framework based, where you would plug in a module that would say, this is an arbitrageur. And this arbitrageur takes these things as their state, and then they perform these actions in this particular order. Or this is a noise trader. This individual comes into the system and there's a distribution of potential trades that they find interesting, but we don't know anything about them, so we model them as a stochastic process. That's one particular way to actually specify a behavior. And sometimes you do need that to close a model that requires something like an arbitrageur bridge to be consistent. Another way to do this is to look at the admissible set itself alone and to say, we don't know what kind of behavior is being done. So instead, what we're going to do is we're going to build sequences of actions of things that are allowed, that are feasible, and just let them run. And if we feel that maybe one particular sequence of someone, for example, continuously withdrawing from the pool one asset could be one direction, then we could use that to assess whether or not the system is stable under the condition of somebody attempting to drain the pool. Does the price go to a high enough level that then doesn't become something we need to worry about, for example? Or random sequences of things drawn from the admissible set. When is it that if we have clustering of different types of activities, Is there some hysteresis where if you cluster them in one order, you get a different outcome than if you cluster them in a different order? That would be one other way to do this. And there it's more behavior free because you're really leveraging what the admissible set is. The trade-off is you have to do a whole mess of that in order to be able to get a reflection of the things that can happen from the system, as opposed to if you were super confident about one behavior, putting that behavior into the system. And the reason that we don't typically do the latter, although it's a lot nicer from the point of view of saying it's cuts a lot of the experimental workflow out, the complexity out, is that it becomes extremely dependent upon that behavioral assumption you've programmed in.
Yeah, thank you. And so just to follow up on that, so you, as BlockScience, have already established some sort of traders that you'd like to implement in these digital twins, or?
Typically not. We don't. In fact, it's one of the things I think that the HydraDX team has been key about surfacing, is that they would like to be able to have a test suite of different types of agents to plug them in and have different types of behaviors. And I think it's actually quite a nifty idea, and being able to put it into the context of cadCAD as an open source environment, I think it's something that's definitely worth looking at. From our perspective with clients, what we typically do is attempt to build as much of a bespoke solution as possible for what it is that they're looking for. And we typically try to do that without agent behavioral assumptions. So we try to do the hard one, the one where we try to build all of the different types of activities that can occur from an admissible action set, and then ensure that the system maintains certain properties regardless of what can occur.
Yeah, okay, cool, thank you.
Sure. Okay, so I think I'll stop my side of the presentation now and jump over to Chris, who will then show you an application of this workflow within the cadCAD code for the Hydra system.
Perfect. Thank you, Jamshid. Thank you. I think that it segues perfectly into my presentation, the last question that you've discussed, because I would like to start my explanation of the process with one particular action sequence that we've selected for the agents to perform always in order to be able to test one particular question. And the question that we were addressing first, and I would like to walk you through in the explanation, is the question of how to assess impermanent loss. So let me share my screen now, and let me show you the action sequence that we've decided on defining. So the experiment setup that we did for our experiments was basically to incorporate two types of agents into the cadCAD environment, which would be one agent would be the liquidity provider agent, and the second agent would be the trading agent. And what we wanted to do is to perform an experiment with 100 time steps where the first agent, let us call him agent A, would provide liquidity in a risk asset at time is equal to 10, and he would remove his liquidity at time is equal to 90. And agent B, the trading agent, would just swap randomly in between the two risk assets in the pool, so the RI and the RJ asset. But we wanted to incorporate different possibilities for him to trade. So we varied the sizes of the trade, and we varied also the direction. So it was not always the same size, and it was not always I for J, R for J, I for J, but it sometimes was I for J or J for I, respectively. And how this is reflected in the code, there is one file which is called the action list. And you can see a snippet here. And this is exactly the random sequence that we defined. So you see that if there is a particular parameter selected, which is the random sequence parameter, and if it is on, then this action sequence is performed for the cadCAD execution. So you see that at time step 10, you would see this test add liquidity event. You would see that the asset that is being added is the asset I, because the random choice of only one variable is this variable always. And at time step 90, you would have the test remove liquidity event, again, with the variable I. In between, so for all other time steps, you would have agent B doing the trades for the in a different direction and for the different asset choice. What we wanted to perform and what we wanted to test is how one particular choice of parameter will affect the experiment results. And Jamshid has been talking a lot about this in the previous section. But the parameter selection under uncertainty was performed on the parameter A in this case. And the parameter A is a free parameter that is incorporated or encoded in the R for R swap mechanism. So in the current mathematical specification of the Hydra cadCAD model, if you look at actions that are trading risk assets, one risk asset for another risk asset, you would see this formula being applied. So you see that the size of the other asset that is being added or removed from the pool, depending on the direction that you do, depends on this parameter A. So there are some coefficients, there are some the amount of the asset that is being performed, that is being provided, but there also is this parameter A in this equation. And we wanted to test how different values of this parameter A will affect the dynamics of the pool. So what we then did was a parameter sweep which covered the different values of the parameter A. So here you see 0.91 and 1.11, which is here again reflected in the snippet from the code that there is one particular file which is the which covers the parameters of the simulation, and here you can select or define different values for the parameter that you're about to sweep. So you see here three different possibilities. The hash means that it is commented out. So you see that we actually have chosen this definition for the simulations, but there is this possibility of only passing one parameter to cadCAD. So if you activate this line instead of this one, you would have no parameter sweep. You would have the model executed and performed only with this one value of A is equal to 1. If you hand over this vector of A's to the simulation, then you would have not 3 parameter values, but you would have the model executed 10 times. I think it's 10 or 11 times, where each of these values are being swept over. So this is how you can define parameter sweeps in one particular file of cadCAD, and I will show you this. So what was done then was a set of Monte Carlo experiments with 10 repetitions each. So for each of this parameter value, and for these varying trade sizes that are being drawn for a specific distribution that we defined, there were 10 repetitions performed with each parameter value. And the trade sizes that are being used for these Monte Carlo experiments are defined as well in this parameter file of cadCAD. And you see that here you can define the mu, which is the mean of the distribution, which is the expected value. This is the trade size that we want to have, and it is varying with the sigma of 50 around it. And obviously, you can define different mu's and sigmas to see how this choice of random traders coming in, so an external factor, as Jamshid described before, being prescribed to the model, and having someone who is trading randomly with random trade sizes, but roughly around 1,000, how this behavior, so to say, would affect the results of the model. So, as we discussed in the previous question, in the current setup or in the current experiments, we didn't have intelligent agents incorporated that would do particular actions based on previous state or conditions on different metrics, but we much rather prescribed particular behaviors and prescribed particular sequences that were always executed whenever the model is run. And this led us to an experiment setup, which is a testing table of all of the experiments performed. Sorry, and you see here that these would be the experiments, the 60 cadCAD runs that were defined before. So you see that the first cadCAD runs, the run 1 to 10, are with the parameter value A is 0.5, or I think 0.9 maybe. So maybe this is an old table, but 0.5, 0.9, with the different parameters that are here defining the initial conditions of both liquidity pools. But for this block of experiments, we held the initial conditions of the pool amounts constant. We said there is always 1 million assets in each pool, but we are about to vary the trade sizes. We also performed experiments which we called block 1, where it was the other way around. So we varied the initial conditions in the system, but we fixed the trading sizes. But in this experiment, so in this battery here, we had the scenarios where always the pool amounts are fixed at 1 million in the beginning, and the mean of the distribution is at 1,000. And for each value of A, we performed 2 tests, one with a small sigma and one with a big sigma. So here we would have trades varying really around 1000 with only small deviations. But here in the second case, we also asked how about the trade sizes would be a little bit broader. So this is what was the setup, and I want to show you first in the notebook where to set these things, how to use the tutorial to incorporate these different tests and these different setups. And I also want to connect a little bit to what we've discussed in the first lecture. And in the first lecture, we motivated our whole cadCAD modeling journey with this diagram. So as you can see here, we identified different metrics or different things that the liquidity provider would look at. So the blue circles. Here we identified different metrics or states that the trader would look at. Then we identified some parameters that we can choose or some things that we can design, which are the yellow circles. So here we have this parameter A that I explained just now, which is a mechanism-specific free parameter. We didn't discuss this in the first lecture, but I told you that there will be something coming that we might be able to select, might be able to choose, that will affect the performance of the system. Here we also have the fee parameter. This is what we haven't even been talking about yet, but this is something that we want to look in the future for the next lectures, where maybe you would like to say, now I know how to select the parameter A. Maybe I can now design something that would be the fee parameter that would affect also these kind of metrics, and that I want to see how this can be incorporated in the model. And capital efficiency, this is where we very briefly talked only about where we said we assume very intuitively that since we pool all assets together in the OMNIPool, in contrary to a wide variety of pools in the Uniswap context, we assume that the capital efficiency is higher, so we will attract more liquidity volume. But what Jamshid also addressed in his presentation is that you have these different effects of the parameters to different metrics, and you see that if you increase the fee parameter, you would have a positive impact on the ROI, so something that is a positive experience for the liquidity provider, but you would have a negative impact on the trade volume. So you see this happening here. And at this stage where we had only this causal loop diagram, we were not very able to make any quantitative decisions or any quantitative assumptions about how the model will perform. But now, having fixed this in our mind, we can transition to an implementation of the model, and we can say, let us really look at how these things can be assessed once we have the model. So let me very briefly show you the OMNIPool model tutorial. So this is a document that I provided to you last week already. Maybe you have had the chance to look at it very briefly, but if not, I encourage you to use it now for the future experiments with the cadCAD model. And it explains very briefly in the first section how the model file structure can be used and where to find things that you would like to change. So here in this first section, you see that each of those files here is explained and what's happening there. And if you look at the model that you are probably also having been looking at, you would be able to find these respective files here, and you would be able to now know if you compare it to this tutorial and see, okay, these are the things. Here is the place where you would be looking if you want to change, for example, an action sequence or a parameter or whatever. In the second section of this tutorial, I encourage you to try some things out. So for example, you can go to the file model sim setup file, where you can choose the simulation time steps and the number of Monte Carlo runs. So if we go here to the simulation setup file, you see that if you open it, you define the simulation time steps. Here I have it at 100, and you can choose the number of Monte Carlo runs, the repetitions for the battery of experiments that you would like to perform. If you select here only one, then the model executes only once. If you select it 10, then you have 10 runs, and then you would be able to see, according to the Monte Carlo logic, how this distribution of your external processes affect the dynamics of the model. The very next thing that is very important for you to see or to try out is the action sequence. So actually, which inputs or which action inputs, which events are triggered in the model, because this is what you want the model to do. You are able to go here to the file action list. So this is here, model action list. And here at the very top, you can define this random sequence that I snippeted out in the presentation. So this is where you actually can change things, and you can change the time steps at which things happen, or you can change the event, you can change the action. So you can say here at time step 10, you don't want to test a add liquidity event, but you would much rather want a remove liquidity event, right? So you would want to have it happening twice at the time step 10 and 90. You can overwrite it here, and then you would dictate the model what to do at this time step. This is explained in more detail here, so you can read it through, because there is not only this action sequence that you can change, but you can really map different activities of the agents or different types of trade that they would be supposed to perform. So if you see here what is explained here in the test for R, Q for R, test for R logic, you can go to the very bottom of this file, action list. And here you can say, at this point, the direction that is being selected is always test R for R. So this is what is the active line in the code. So an agent will always exchange one risk asset for another risk asset. But you can overwrite this, you can change it. You can say, no, I'm not trading R for R, I'm trading R for Q. So someone is coming in and is trading a risk asset in for the base asset, for the Hydra token in return. Or alternatively, you can say, I don't want to prescribe this one particular action to be happening all the time. I simply want him to draw this by random, so I can even test a vector of different possibilities, and I can say to the system, please select one of those actions randomly, and this is what you should then, or the system should perform at this given time step. Here you can change the system parameters. So there is this file sysparams that is open here. And here you can pass different parameters. So you can prescribe. So if you don't activate the action sequence parameter, if you don't prescribe an action sequence, you can dictate exactly here in this file what will happen at each time step. So if in action list there is nothing here, right? So if you just erase these parts of code, then the system would always at each time steps perform an R for R trade. Or you can dictate the liquidity action that is being performed at each time step. But you can be more sophisticated, right? You can say, no, I'm defining an action sequence because I don't want the system stupidly to do everything the same all time. I want to do more sophisticated stuff. The trade size you can dictate here. So you can say, if you want to vary the size, you just you tell the mu and the sigma of the distribution which is being drawn from. And other different parameters that you can use, which we won't talk them through now, but you're free to open this file and have. I was very elaborate on the explanations here. Here, as promised, you can also define the parameter values for the parameter suite. So you can say, I'm doing only 1, I'm doing 3, I'm doing 10 or whatever. So as many as I wish. And here also in the last remainder of this file, some initial values are defined of the pool, but this is not for the parameters. Here at the current stage, you have fees defined. So now we have no fees. So we have a fraction of each trade, which can be deducted from each trade, which in this case is 0 because the numerator and the denominator cancel out to 1. But what you can, the parameter suite I already explained. So by simply going to this same file and just replacing the vector of A's with different values, you would be able to execute the parameter suite. You also can change the agent initial token endowments. So you can tell the system with how many tokens of each risk asset each agent is equipped. And you can do this here, but we won't elaborate on this in this explanation, but you're free to do this on your own time. And now finally, changing the mechanisms, you can do this as well, but be careful about that because you have to be very, very sure what you're doing here. I just wanted to point you to where the mechanisms are defined. Okay, so let us now look into some notebooks that I've prepared. So at first, I've prepared one notebook that is performing or has been run with this setup of the experiments with that we showed in the slide. So there are these different values of A, which is not true. Again, this is 0.9, 1, and 1.1 because if you look at the simulation, it's the system parameters, then you would see that that they are defined as here, right? So 0.9, 1, and 1.1. So this table actually is not correct, but nonetheless, the other values are still the same. And then if you run the model, then there is the code that is required to run the model. You see the results data frame. So you see now that the initial conditions are 1 million and 1 million in the other pool. You see that you have different trade sizes here drawn from this distribution at each time step. You have a different direction drawn at different time steps. And you always have, besides the first variable one time step, which is the just initial condition time step, which Spartan explained last time that we are about to neglect for the simulation purpose. But starting from this one, you see that every time we have this test R for R trade direction. So these things are actually happening at these different time steps. And then you can just look at the results of the data frame. You see which columns the data frame has and which variables are mapped there. Then you see how many time steps have been performed. You see how many runs have been, so 10 Monte Carlo runs. And then you see if you want to access results from one particular Monte Carlo run, you can just select the number of the run here, and then you would have it visualized here. Then you see the starting balances. As I told you before, we restricted in this block of experiments ourselves to only have fixed starting balances. So therefore we have 1 million always for the left pool, for the I pool, and also for the J pool. But for the trade sizes, we have a wide array of different realizations from the random distribution. So you see here that this is actually varying between 850 and 1,020. 1200. So, and what you then can see in this notebook is all of the liquidity dynamics of all of the variables. So here you see, for example, what's happening on the base side of the OMNIPool, where the variables H, Q, SQ, and Y are plotted. And here you see that there are always, for each parameter sweep, there is one plot produced. So you see here that this is a scenario of 1.1 for A. Here is a scenario of 1.9 for A, and here you see the scenario of 1 for A. And here you see in this different plots, you see how the liquidity variables of the base side of the OMNIPool are performed over the simulation. Here you see a fan plot. So here is the same situation as above, but here a different type of plot to see what's going on for the base asset Q. You see that there is, after the liquidity add event, there is some liquidity being included in the pool, so more liquidity at the pool. At here at time step 90, you would see the removal. And you see a fan, which is not so very well visual here because we have, but I will show you with the risk assets in much more clarity. Here you see the effect on the asset H, which is basically tracking the same as the variable Q. So there is supposed nothing to be different. Here you see the shares of the base asset, and here you see the Y parameter, which is a pool-specific parameter. Then you can switch over to scatter plots just for your visualization preferences. I've included one notebook in the demonstration repo where you have all of the plots visualized. So for you to select which one you would prefer best, but we will skip over this now and let us move over to the Hydra side of the pool. So here now you see that the risk asset in the pool, and you see visualized here the amount of the risk asset, and you see visualized the shares of the risk asset vary because we have now the liquidity event here at time step 10. So actually liquidity is injected at time step 10 to the pool, and it is being removed at time step 90. So this explains this huge movement here. And in between, there is another agent coming in and trading randomly. So this explains this going up and down here over the course of the simulation. And since we did this experiment not once, but 10 times, we performed this experiment 10 times and visualize everything in this one into one plot. Here you see in addition the max and the min values of all of your Monte Carlo runs. So here the blue dotted line is actually the mean value of your Monte Carlo runs. And here the top and the down are the mix and min values. So you really see what's going on. And
just quickly to interject, just to follow on what Henrik had mentioned before, here is a place where you could, instead of using the max and the min, just use the deciles. So get yourself to a 95% of the mass, and then start to build frequency distributions on how far this might project off going up or going down, and give some sort of an assessment for the risk management. Sorry.
Super, thank you. And here again, you see that each of these realizations is plotted for the three different scenarios, A, 1.1, A 0.9, and A 1.0. And then you can move over to the risk asset J, which is the other asset in the pool. Here you don't see these jumps up and down because the risk asset J is not being added or removed to the pool. It is only the one which is being traded randomly between the risk asset I and J. So therefore you only see the trading activity happening and not any liquidity events. Again, for 3 different realizations of A. And that's about it, because then we move over to scatter plots again for you to choose which realization you like best. As you see, there are different, maybe it's for you just to understand why scatter plots are so maybe interesting to look at, because you see that here the max and the min values, they hide a little bit what's going on in reality for one simulation realization, right? So in between, you don't really have nothing here, but on the fan plot, you would only see the max and the min as it is currently visualized. And then finally, there are 2 plots that show you the prices in the OMNIPool and the price of the asset I in the pool, and the price for different values of A again, and the price of asset J in the pool for different values of A. So then I prepared 4 more notebooks, and the 4 more notebooks are short ones. So they are short because I removed all of the duplicate plots. And here you would see that we again have the experiment, but this time it is, I remember, yeah, it is run with a sigma of 50, and it is only one run. So if you choose the Monte Carlo parameter here in model part simulation setup, if you just select it here to 1, what would happen? You would get 1 single run only, and then it looks like this, right? So you don't have any this fanned out visuals going on because there is only 1 realization for each time step. If you move over to the Monte Carlo realization to this notebook, you would see what we've already shown before in the longer version of the notebook. So you would see that it is showing really the realizations of each run, and therefore you see that there are more things to show and there are overlays in the data. And here you have this additional information that you gain from running the model multiple times. And then I ran the model not for the sigma 50, but I ran it for sigma 500. So here, if you just select again, as we said, in the sys params here, you can choose to run it not for 1050, but for 1500. Then you would get different time series in the results. Again, for 1 single run, it would look like this. Let's look at this, because this is actually the most important things. The histogram for the trade sizes you see here in the previous version, you would have varying around 1000 between 800 and 1200, and now we vary between 0 and 3000. So for one realization, you have it looking like this again, right? Different results, and for Monte Carlo run, you would have it looking like this. So this is for you just to try out. So I think that if you are now take the notebooks that I've prepared, and if you take the tutorial, then you can start really exploring what's going on by combining your different ideas, changing the action sequence, changing different parameters, and seeing how the model how the realizations will result in manifest themselves in the notebook. Let us maybe try one such parameter change. So maybe let us go to this one template notebook that I prepared here that would be executed, but maybe only for, let's say, 2 simulation runs, because it is a little bit time heavy to run more. And let us save this change. And
Chris,
yeah,
just ask the notebooks are called experiments here. The ones you had in the tutorial, weren't they called example? Are they the same? Or
they have to be the same, I guess. But I think, let me see. I think that notebooks are also called experiment. Maybe it is different. Now let me see. I added new notebooks. So if you look at the model repo now, you would see the experiments notebook and the example notebooks.
Okay.
Right?
Cool.
So there are multiple notebook here to choose. And over the course of this week, I've added those just for you to be able to experiment with these. With these as well. So let us go to the action, no, not to the action files, but to the sim setup. We just changed the number of Monte Carlo runs to 2. We changed the parameter, let's say, to I don't know, 100. So we can do this here, and let us also change the parameter sweep to not these values, but let us make only maybe 2, and let us make something like 0.8 and 1.2, and then remove the rest here, then save it. And if we run this notebook, clicking on here, let me see here, then what would happen? I think it should run very quickly because we have only 2 Monte Carlo runs.
Chris, may I ask you, these are the first tests that we did for assessing the stability of the pool, or are these already the impermanent loss assessments?
These are the tests that we did for the in between. So these are the block 1 and block 2 experiments that we described to do the parameter selection under uncertainty given the metrics. But what I didn't show you now, and I think that this is because of the lack of time that we have, is the parameter assessment itself. So there are no metrics included in this notebook. So the process that Jamshid described before was the full circle, going from goal definition over mechanism design, system parameter identification, to selection of parameters given particular metric realizations. And what I showed you today is only how to describe different experiments, how to set them up, and how to run the notebooks without looking at different realizations given the metrics yet. So this could be something that we could cover in one of the future discussions. But what I very simply wanted to show you here is that since the very most important change for you to see, since we've changed the parameter sweep to only 2 values, each plot only shows 2 graphs, right? So there are not 3 as before with 1.1, 0.9, and 1. We have only 2 with 1.2 and 1.8. And since we have only, I think, 2 Monte Carlo runs, this is okay, you don't see it here in the fan plots because it looks the same, but if you would see the scatter plots would only have 2 different realizations. So this is about it. So this is what I wanted to show you today. I think I hope I covered a lot of ground for you to be able to start exploring and start leveraging the tutorial that you have and the notebooks that we've provided, for you to get creative with your own experiments and really see what's going on in the system, and maybe starting asking your own questions and asking how these questions can be addressed given the framework that you have now with the simulation model.
Actually, just to follow quickly on that, thanks. And that was, I hope, very, very helpful just to figure out what it looks like when you actually do these things, but also just quite important what Jakob had mentioned in terms of looking at the results. Some of the metrics don't have to be fancy calculations of things like slippage and impermanent loss, although we do those things for assessing the system goals. Things like system stability, you may just want to see whether or not the reserves run off to infinity or to 0. And in that case, then the results themselves may be describing for you the system stability properties, which is, I think, maybe what Jakob was alluding to there, that what you're actually presenting there, Chris, is in a way an assessment with a KPI that's sort of degenerate. It's just what is the balance of the reserves that are present there. So it is nice to be able to see that you can glean something from the results that you're seeing about how the system is performing and relate it to a particular system goal that you may have in mind that may be very simple to articulate. Nice. Any questions?
Yeah, any questions? Yeah, maybe if there are any questions before I hand over back to Jamshid for some final comments and discussion. I take that as a no. Jamshid, you're free to continue.
Thanks. Thank you, Chris. Thank you for that component of the actual parameter selection process that we do. And so we've now gone through the gamut of the way in which we are using the system. And so what I'd like to do is to kind of finalize things both with an invitation, but also a description. And this kind of harkens back a little bit to some discussions that have been going on in the Discord channel and maybe in one of the Tuesday sessions about mechanism design itself. What is it that you actually can do to build the mechanisms that you are then testing? And remember that we've gone through a lot of descriptions about things like the requirements, like the goals that we have, but we haven't really discussed a lot about how you derive mechanisms that you then are going to go and parameterize and test. And so just in the very little bit of time that we have, I'd like to kind of step through a little bit of the some of the indications that, particularly for AMM environments, give one way to think about how to build a mapping between what you want the system to do and what you in the end choose as the class of mechanisms that you hope one or more parameter values associated as an instance of that class will support in some fashion the KPIs that are associated with those system goals. Because that, in a sense, is the last bit of the design process itself, the actual designing that goes into the entire engineering framework. And there are as many different ways to do that as there are engineers. In fact, there are as many different ways to approach the problem as there are scientists. And so I'm just going to provide one particular direction that is useful within the context of the class of dynamical systems that we've been engaging with so far. And I'd like to tie this then formally to the notion of an invariant or invariance of a system. And the observation is, and it's just an observation that may or may not apply to a system of interest, is that some of the system goals that you articulate when you are designing a system don't change over the time frame that the system is expected to run or to be live. As an example, you may have a system goal that says that the AMM pools should not run out of funds. So that's a system goal that is the same day after day after day, depending upon how long you go. It doesn't matter. You want that system goal to be retained. Another one that we pull out of the Bitcoin network would be that the total amount of Bitcoin accounted for should be equal to its supply. And notice that it's not a tautology because we're talking about accounting on one side, so no double spends, and then the actual supply on the other side of what's been minted. And you'd like that particular equality to persist for all time. Another example, which kind of gives us that a little bit of a flavor of risk management, in fact, the next two really do, the probability that price volatility exceeds 10% of the price level for more than 1 hour is less than 1%. So this would be kind of a beginnings of a risk management idea that if you had a situation in which volatility was exceeding that amount of 10% of the price level, that you would want it to be longer than 1 hour of exhibiting that type of volatility, less than 1 out of 100 times or universes that would exist. And finally, another example might be something about security, network security. The cost of taking over 51% of the network, suitably defined in some fashion as to what control means or what taking over means, should exceed some amount, say 100 million US, at least 99% of the time. That would be then for realizations of the experiment that is being run, that is proxying for the universes that we see, that 99 out of 100 of those universes, it would cost at least that much money to take over the network. So these are different ways in which we can think about system goals on the one hand, as articulating what do we want the system to have as properties. On the side that we say, okay, these are nice, but are these things that are going to change tomorrow or the next day? No, we'd like them to be things that are persistent, that persist over the lifetime of, and then you define kind of the lifetime of an exchange or the lifetime of a transaction. So for example, if you're looking at miner extraction value, look at how the miner is rearranging transactions. So within a block, if you're looking at things like the draining the pool for an AMM, you would like it to be over the entire life of the market that you've created, for example. So goals themselves that don't change over time are, by their definition, invariant, and that invariant term becomes a leading term to try to explore the properties of the system that themselves entail this kind of invariance of the system goals. So it's possible, in many cases, to express the invariance of the system goal using a relation or relations, that when you are looking at that condition or that horizon or that location for the system goal's applicability, imply invariant properties of the system. These are things that you can calculate or things that you can compute. So we move from the idea of the system should never run out of funds to some sort of invariant property that when we actually observe that property, we then know that the system will not run out of funds. Constant function market makers like Uniswap and Balancer make use of these types of formal invariances to be able to do this type of reinforcement of a system goal. And we'll see an example of that in just a moment. And generally, because invariance is a form of symmetry, and I'll try to tease out a little bit of that in as short a time as possible to show you what a symmetric environment gives you invariance, what that looks like. That allows you to attach through things like this amazing association via Noether's theorem, the ability to look at symmetric environments as things that are conserving something that has been defined by this. This invariance is actually a conservation law dressed up or hidden. And the idea then is to uncover this, and in so uncovering, be able then to state that these system goals that are not changing over time are not changing precisely because they are mapped to that property, which is being conserved. So that property is carrying that formal and equivalent invariance with it. Okay, so just as a quick example of this, let's suppose we were looking at the Hydra AMM with swap invariance. Let's suppose that we have an operation, which you have in the code, the actual operation that shows when you provide, for example, asset I and receive asset J in the market. There is a formula for that that gives it exchange. And let's think about that swap operation not as I put in I and I get back a quantity of asset I and I get out a quantity of asset J, but rather that I perform the swap operation. And what happens is that the state of the system was in one state before, and now it's in a different state. So think of the swap operation as performing a state transition. Now, of course, we know that the state transition is one of the reserves went down and the other reserve went up, and then something else may have happened in the middle. But let's think about it as a mapping of, in the GDS framework, from a state X to another state. A system goal that you might associate with swaps is that without fees, swapping between two assets, I for J and then J for I, should recover the same system state as before. And so, and there's a question noted there about the invariance holds without fees. That's correct. I'll come back to it in just a moment. So system goal is without fees, swapping asset I for J and then immediately swapping J for I recovers the same system state. So in the semantics of the swap operator, that means that given a system state that we will call X, if you then perform these two operations in a row, starting from X, you get back X. So that's the invariance or the symmetry of the system that's being defined. And in this particular model, that swap operation, the formula of which Chris actually showed you in his demonstration, that's actually derived from a form of, in fact, a generalization of a constant function market maker framework that was developed by the HydraDX team. So you have this ability to kind of use as a principle, a guiding principle, this ability to understand that this invariance can be treated as a symmetry. Now, there's another system goal here, which is that, let me make sure I haven't skipped slide. Yeah. Another system goal here is to incentivize, for example, liquidity provision by liquidity providers. A candidate mechanism that you might think of is to say, well, I've got my system without fees, and I have my invariance that I have without these fees. Let me introduce a fee, a swap fee, a transactions fee for trading. A portion of the swap, either in or out, is either added to the reserve or remains in the reserve, depending on which end of the trade it's actually occurring. Now, a larger asset pool increases the return to the LP's shares, as we described before, a little bit earlier. This idea that because they are holding shares of the pool, that's a right, a claim on that share. As the reserve goes up, they get a higher share, the yield goes up. And as we mentioned before, in that trade-off with system goals, a swap fee disincentivizes traders from using the swap mechanism because it's expensive. They don't get out as much as they actually were expecting to get out. And so the system goal trade-off then is this balance of the yield, the return to LPs, against the slippage of the trader swaps. Now, as was observed already in the chat, and as it's important to drive home, there is still a connection to invariance, but it's one step removed when you introduce things like a fee in the system. The fee itself generally changes the state of the system, so that if we actually made the swap operation dependent upon a fee mechanism, we'll call it phi. Actually, in Greek, it would be phi, in fact, but then we would have to call pi, p, and all of that. So let's call it phi for the moment. If you parameterize the swap operation by phi and then perform its inverse, you generally get a different state. And that's because of the fact that the reserve itself has changed size as a result of the fee being put into the system. So instead of viewing invariance simply as a global system property, you use it as a guiding light. You use it as a trajectory forward to say, well, let's look at the system goals that reflect the properties that I find interesting, but recognize that there are other things that we have, other system goals, like the ability to provide a yield to the LP, like the ability to provide a yield to the LP that does not sufficiently disincentivize traders, that allows you to view the invariance as one or more types of limiting cases, like a zero friction environment of the definition of a system. And so this is one of the pathways in which mechanism design can be performed, and there are many others. You can look at the system as a gigantic system in which you are looking for impacts that will occur according to very, very large integrated with a fee mechanism. Or you can start with a system that is separable, where you separate the invariance when the fees are zero, look at that invariance, understand it, and then build the fee back into the system and examine its implications. So just as a teaser for those of you who are looking forward to your research project starting from next week onward, here are some open research questions around this disentangling of the fee mechanism within the context of the Hydra AMM. So one of the questions you might ask is, does there exist a fee mechanism that achieves all of the system goals for the Hydra AMM? Now, I've been leading you down a primrose path, but the answer that you might be thinking of is, well, no, that's probably not possible because you need to balance the different system goals, at least from the LP and the trader. So perhaps it's possible for you guys to come up with something that would achieve all system goals, in which case, more power to you. If not, which criteria should be used to select among those different candidate fee mechanisms that you are investigating? Should you go back to invariance and maybe try to generalize the symmetry or lift the symmetry up to a different level? Should you apply different types of metrics that will give you information that will allow you to assess in the parameter selection under uncertainty workflow different classes, different instances of fee mechanisms, and even from different classes? Metrics like slippage, impermanent loss, opportunity cost. What is it that the next available operation would allow you to do? Different types of mechanisms will afford and naturally surface different types of metrics to be able to assess between different realizations of these mechanisms that are created. And that's also part of the research process, to be able to generate the metrics that make the most sense for the particular mechanism that you're introducing. Now, it doesn't go unnoticed by the rest of the system. The rest of the system depends upon these things. So one of the other questions you would be asking is, well, all right, I've changed the fee mechanism, I've plunked it into the system. What happens to the rest? And in particular, what happens to the rest of the system? What are its consequences of the introduction of the fee? Are other system goals disrupted beyond the ones that I thought? And the reason that this is important to address is because the system is complex. And sometimes there are feedback effects that will occur on the basis of the system's configuration itself, or getting back to one of the earlier questions in today's session, on the basis of what people think will happen when you have put a new mechanism into the system. And so people's perception of an introduced fee mechanism can also change then the system goals that are coming out. And then it is important to start thinking about the behavioral implications of this in perhaps at first as loose or as general a method as possible. But gradually you start thinking about professional traders or people using a price oracle or arbitraging across different AMMs, and you recognize that there may be some behavioral assumptions that are strong, but maybe for that particular system goal you are interested in are natural to explore. Should fees themselves be static? Should you just have a fixed proportion a la Uniswap of the trade? Should it be dynamic? Should they be a function of the state of the system? Think about that for a moment, this distinction between having a static fee and a dynamic fee. A dynamic fee is, in a way, infinitely more degrees of freedom with both the costs and the benefit that entails. But in a sense, it allows you to much more accurately track what might be considered a best trade-off, if we continue to use the straw man of the straw person of the liquidity provider and the trader, balancing their yield versus their ability to conduct a swap, for example, accordingly, then that trade-off may be something that you can actually find a metric that helps to minimize the loss to both if the fee is allowed to change not necessarily just its value, but also perhaps even how it depends upon the state over time. So perhaps a very broad research topic, but moving from a static fee to a dynamic fee, I think, is something that is both on the cutting edge and the forefront of most of the AMM systems under scrutiny today, and also is something I think that the Hydra AMM system would benefit from at least having one or more groups investigating in more detail. From the point of view of understanding, is it possible that something I really created that is fantastic, that fulfills these criteria, is it possible to actually write this into an implementation? Well, that becomes another question. What are the computational constraints that are present? If you're going to move something from Python, which is a fantastically strong language for expressing mathematical relationships, into something like Solidity, well, there's a mapping translation that needs to be done here, and there are computable complexities, computable constraints here that then bind when you make that passage, or might when you bind. And finally, given the class of the fee mechanisms that you have, is it possible to represent that class in a way that allows the parameter selection under uncertainty process to be performed in a parsimonious fashion? And what I mean by that is, do you have so many parameters for your mechanism that the parameter sweeping space, the dimensions over which you have to parameterize, blows up? And then it becomes very difficult to get qualitative or quantitative conclusions about the balancing of different system goals for parameters that you have estimated, simply because the parameter space is too large to search over. And there again, you kind of find an art form where you're trying to develop the class that still represents what you want in that fee environment, in this particular example. But at the same time, you want to make sure that the way that that class is represented can be done so efficiently in a computing environment. So it's not necessarily a question of hard constraints when going to a live system. It's more about the curse of dimensionality, that the system explodes in dimension far too large for you to actually make meaningful conclusions on the basis of which parameter constellation you want to choose. Okay. I think I've hopefully touched upon both a way in which it is possible to understand mechanism design from that particular lens of invariance, which is used quite often in AMM analysis, and at the same time make a soft pitch for those of you who are interested in fee mechanism development within the context of the Hydra AMM, which I think is extremely useful and will be one of the low-hanging fruits for moving forward, I think, in generating conclusions. Any questions before we wrap up?
Now's the chance. Anybody itching to ask questions about the modeling or the topic from today?
Food for thought.
Cool.
Okay.
I would have one question.
Sure.
Is the influence of fees on the invariance as proposed by Hydra already researched?
Not to my knowledge. I will let the Hydra team answer definitively, but not to my knowledge.
Okay.
No.
Okay, there we go.
Question answered.
Very good. Okay. Let me try now to tie up and wrap up the first 6 sessions that we've been going through today with where we are going to move forward for sessions 7 through 12, because they are not disconnected. It is not a hard break. It's more building upon what you have seen and helping to enable where you are going to go. The next steps for next week, session 7, are for you, the participants, to be able to present to the rest of the audience possible research topics that you are interested in and exploring from sessions 8 through 12. This is a brainstorming session. You'll do a little pre-brainstorming, and I'll mention that in just a moment, but individuals or groups of participants, but I would like to bound that at 3 because that's the feasible limit for this course, presenting maybe 1 or 2 topics of interest to all participants for discussion and feedback. And I don't mean a formal presentation. I mean more, this is our idea. What do you think? Now, the topics themselves should be connected to the HydraDX AMM in some fashion. If you are not certain, you have a fantastic idea that you think is very interesting, but you're not quite sure how it connects to the AMM, we can see if we can uncover such connections during the discussion that we have next week. And the overarching goal is that by the end of that session, there are research groups that have been formed with a maximum of 3 participants per group to explore one agreed upon topic for that particular group, for each group. So each group has a different topic, and they each then explore that topic. And to assist in this, there's a link here inside the slides, which will be provided to a template, or HackMD, which just kind of allows you to sort of pre-brainstorm about the topic itself. You can feel free to just copy this text into your own HackMD document and then fill out these particular headings of the things like what is the question, what's the description, its relevance, approach, and so on. Again, nothing here is being collected or examined. It's simply to allow you or your individuals that you are now thinking about joining up for a group to sort of think, well, in a structured way, how would I approach this particular kind of research topic? What's my guesstimate as to what it would take if money was no object and time was no object to actually fulfill it? What do I think I could achieve within the time frame of 5 weeks, of 6 weeks? These are kind of the ways to flesh out what it is that will be discussed and surface further in the discussion on the 23rd. So I'll pass that out in the channel. Any questions before we move on beyond that?
Maybe I would like to add that Hydra ADX is a decentralized project, and it has quite significant bounty program. So if a feature or some improvement lands in the protocol, then there will be definitely a reward for that in terms of tokens. And we try to reward based on the contribution value. So it can be quite significant if it's a core part of the protocol. So that's one thing to spice it up a little bit.
Nice.
Cool. And Paulina has her hand raised.
Thanks. To what extent can we use the Tuesday session to maybe informally talk about it? Is there something we can prepare for it? Also in terms of maybe forming groups, seeing where we align.
Yeah, definitely. I was also just about to mention that after this slide, but you're totally right. It's since we don't have homework this week, it's a little bit of a dead spot between the lectures. So I think that would be a perfect opportunity to just do really informal conversations and yeah, see about joining up and then continue that discussion Thursday to finalize groups and decide on questions, ask more questions. So.
Great. I think you probably have a few more announcements, Peter, but I'll finish out just very quickly with a view past that following session to sessions 8 through 11. That's really when the heart of the work would be performed from the 30th of September through the 21st or so of October. Groups can meet then sync or async during those intersession weeks to engage in the research topics. The sessions themselves would then be used to present work in progress to all participants for feedback and discussion. So like, here's where we are now, and to raise blocking issues that can be addressed together. They can be addressed in Zoom breakout rooms. If you want to break out and have individuals hack together during that 2-hour period, we'll be available. Chris and Barlin and I will be available to kind of trill around, as well as the members that can make it from the HydraDX team to be able to facilitate and unblock as best we can. And naturally, during these intersession weeks, please feel free to use the Discord channel. I know that I will be better at checking it on a regular basis to raise queries for sure with the BlockScience team, with the HydraDX team to help facilitate during the time in which you are developing as well. And at the end of all of that, on the 28th, the final session will be group presentations. And there will be a little bit of formality there to kind of describe the problem, describe what you've been working on, describe solutions, directions forward, and other issues, just to be able to ensure that you feel like by the end of this entire 12-week course, that you've actually achieved that type of progression in what you find interesting. And being able to do that feeling of achievement really comes through when you're able to present to a group of like-minded participants. Okay. Well, thanks. It's been really a pleasure to be a part of this, and on behalf of Barlin and of course Chris, I know it was really a pleasure to be on the side of conveying this this process of the engineering workflow, not because it's a box that you have to sit in, but before it's really a landscape that you can choose from, and depending upon the degree of the maturity of the research topic or what you feel interested in or your skill set, you can interject in any one of the different directions of that workflow that we've already described. So thanks very much. I'll turn over to Peter then for the remainder.
Cool. And I think speaking for everyone too, we really, really appreciate the amazing work that you guys have done to develop the lectures, and been an immense learning opportunity for everyone, and it's not over, which is cool. Cool. Yeah. So then I'm just gonna share my screen really quickly to follow up on Paulina's question. So yeah, next Tuesday, we usually have the hack and share sessions, but it's a bit of, like I said, a kind of a dead spot between the lectures. So it's going to be totally informal. Come in and just like ask away any questions that you have to me or the other researchers that are there, and maybe some of the BlockScience or Hydra team might be able to make it. We'll see about scheduling, but that'll just be like very, very pre-discussions for what would happen on Thursday when we can formalize everything and pick the teams. And then I also wanted to send, for anyone who can make it at least, and then I also wanted to send a form around just to get an idea if there might be any knowledge gaps. And if anybody has been, like, if there is a topic or a theme that they've been wondering about from the past lectures that is like a roadblock to actually deciding their research topic, or they don't know if their research topic would be viable because they're unsure about this, just feel free to check the box or add it in the other section, and we can maybe try and have a discussion about that topic specifically on Tuesday to help fill in those gaps. Cannot seem to open the form. Okay. Okay, I will update that and send it in the Discord.
To add to that, sorry that we have not been able to join more because we're launching parachain and also governance. But the next Tuesday I'll be there, and I think maybe also Jakub, and we can do some chat and discuss stuff that you are interested in.
Cool, awesome.
We're still watching and reading those.
Great. Sweet. And then I just wanted to show this fun meme that I made really, but in regards to the weeks 8 through 12, so this is, I think the Tuesday sessions we'll kind of feel out how they're going, if they're productive, and if we want to keep them. But I think they're very similar to what the plan is for the Thursdays in terms of coming together as a group, sharing progress. And one thing that we wanted to highlight that's been really successful and helpful in past research groups is just live problem solving and live coding, maybe working on the math specs, just one-on-one or one-on-two or whatever it is, small groups. And so we encourage you to do it async if you have your research team and you can find time together, but we'll also at least hold this time as an optional for you to drop in if you want sort of a forcing mechanism to get together with your team during those weeks 8 through 12. And yeah, group problem solving is very helpful, as we've found. And then the last reminder so I guess that's the hacking part of the hack and shares. But then I'd just like to reiterate the sharing part, which we'd still really love to encourage, and is technically part of the successful participation criteria for the NFTs. We've had some awesome presentations so far from Rudy and Joe's, Kag, Vasily, Henrik, and Ubuko have all pitched in with topics of their own, from their own backgrounds, and kind of applying it to the case of DeFi or AMMs. And even though we're venturing into the research segment of the course, I think it's still really valuable to explain your or to apply your vision or your language to the AMM and DeFi topics. And it'll just, you never know what it's going to spark in someone else's mind in terms of parallels. So it's really one of the most valuable parts of this group is being able to share that multidisciplinary knowledge. So we really want to try and encourage that. And yeah, just another reminder about that session. So I'll be reaching out to you guys to help brainstorm ideas on what you might want to share or be able to. And hopefully we have a few more of those topics come up in the Tuesday sessions for weeks 8 through 12. And then lastly is this idea of the exceptional contributors. There will be a vote. This is a bit of a plug for the last section or the last presentation day of the course. There's also going to be a vote for exceptional contributors. And I just wanted to pass along the criteria so you can start thinking about this if it's something that you would be hoping to strive for and achieve. It's an additional NFT that will mint for you, award to you at the end of the course. And the awards are given out by a peer vote. So this is the criteria and you'll be voted on by your peers through Discord. So if this is something that motivates you and I hope knowledge sharing and exceptional contribution does, then there's an opportunity for a reward. So very cool. That's pretty much it. Yeah, so then I guess we will see you all at the session on Tuesday for that just informal conversation about research topics or ideas or filling in any knowledge gaps depending on the survey. And oh, Hendrik raised his hand.
I think we mentioned a couple of times or spoke about the governance of the HydraDX AMM. What is anything formalized on that? Because I guess a lot of the dimensions we spoke about today and the incentive structure and what is HydraDX AMM trying to achieve to become the global #1 spot for everything DeFi. I guess there's a lot of debate about are decentralized organizations doing the right stuff, voting in the right way, depending on what the overall goal of the system is. Is there any place where we can read about that, or is that something we have to guess here? Because I think a lot of the questions would relate to that.
I can answer. Currently, we are using the same voting system that is implemented in Polkadot. It's something similar to like quadratic voting, and some conviction is there. But what we would like to do is compare this voting system. We are already speaking with people that are researching. I had also great conversation with guys from BlockScience like Michael Zagram and others. So we will read all of these resources and try to come up with something that's best for the system. Actually, it's a chain, so we can decide how we want to govern the chain and if it should have different governance structures for different parts of the protocol, like AMM should have its own, for example, or like it's shared, like the whole system has governance over protocol upgrades, and then there will be some small parts governing, for example, fees or inclusion of the new tokens to the pool, or lending if says there is lending. This is all to be done. We have this one type of governance that is governing like everything right now, but we don't think this is the end game, and it needs to improve very much if we want to be one of the best protocols out there. So if you are interested in that, then definitely this is one of the topics that will be important.
Yeah, I mean, it was only because I was observing on some other DAO protocols that this is sort of like what's the individual getting out of voting for the system? If you want to conquer the world, Do you really want to reduce your profit? I guess you would if you were true and voting rationally for the benefit of the system. But at the end of the day, it comes back to what's in it for me. So I see some challenge in the DAO structure with token weighted decisions. It was more like, and a lot of the stuff we talked about here actually is dependent on how the voting performs, I think, at the end of the day, for success.
Well, yes, sure. It depends on the actors and on the like founders of the projects. And I know for us that I'm in it for because it's interesting to program in Rust, and it's interesting to tackle all these hard problems, and the money is secondary. Once you have enough, then you can, I don't care. Or I know that my co-founder is the same. So we will try to do good for the protocol and for the people that are inside. But that's I for sure know that this is not the case for all of the other protocols out there. You can see that with the tokenomics that we chose. We were trying to do as low allocation as possible, but we knew that we need money to develop the protocol, so we still needed some part. But if it's going to be so greatly successful and have a lot of contributors and a lot of users, then it doesn't matter really, because it will be even very small part of the protocol is enough to be able to focus on what you like.
Thank you.
All right, last chance for questions. Cool. All right, well, we will be in touch on Discord and hopefully see everyone on Tuesday. Thanks again, Jamshid and Chris.
It was a pleasure.
Thanks, everybody.
Bye-bye.
Bye.
Ciao.
Thanks, guys. Bye.